Hello, everyone. In this video, I would like to talk to you about local area network, 802.3, CSMA CD, Ethernet, and 802.15 token ring. My name is Tae Oh. I'm a professor at School of Information at the Rochester Institute of Technology. And this is the outline of my talk. I'm going to talk about the local area networks, Aloha, Salado Aloha, and CSMA, IEEE 802.3 CSMA CD, and IEEE 802.5 token ring as well. Let's then talk about local area network. All of you use some form of a local area network when you connect your computer, your Wi-Fi, and also Ethernet cable connect to your computer when you use your internet, and you are going through a local area network. There are a certain number of stations. They could be a small stations, or station means your computer, laptop, or whatever. And there could be tens and hundreds. It's made for very scalable scale. And the diameter is a few kilometers, usually located within the building. When you connect Ethernet to your computer, that's going through a local area network. And it has a high bandwidth, several megabits or more. And local area network is a private ownership, probably in your case is owned by 성균관대 University. And it's a homogeneous user community. Everybody uses the same protocol, and the local area network being used by everyone there. Okay. And one thing about local area network is a random contention for shared medium. There is a medium. If you want to send anything or ping anything, it needs to be a contention and try it. There is no assigned slot when you send a package or anything like that. It's a randomly contend for it, fight for it, and to get access of the medium, which means send a packet using a MAC protocol. I mean, there are a number of reasons. When you look at even the wireless access, it's mostly a contention based. Thing is, you could assign a fixed access to slots for each computer, but a lot of that is being wasted. You don't know when you were sending a data. It could be idle. You could use frequency bands or time slot to assign to each devices, but a lot of that could be wasted, not even being used. So it's not a contention based. If it becomes very inefficient, and because the local area network data is typically bursty, and it's not really good to assign a time slot or frequency band for it. The topology is usually a bus or dual bus or ring or dual ring stars. And the topology can be different from a physical topology. Most wired local area networks are using internet. Here's the different pictures of topology I was talking about. Is most of your facility you have probably have a bus, something like this. Your computer attached to it is shared between this is a medium, right? If each computer wants to communicate, and you want to make sure that all the computer does not using the medium. Not everybody can use the medium at the same time. So if two or more try to use the medium same time, what happened is a collision occurred. So it's randomly try to access the medium, and there is an algorithm for being successful, and that's the downside of it. And this is more of a ring version. Is that you go around the circle, and each device would have a chance to send the data. And for example, I'll be talking to you a little about it. It's a token ring. If you gotta have a token to send any of the data for any of this computer. So there's a star topology. This is very common star topology here. Basically, it's not a ring. Once the data is coming in, it's connected, it's sent straight to the computer based upon a MAC address. Okay, this is a dual bus. As you can see, there's a medium here, medium there, and one of this medium could be going this direction, or the medium could be going that direction. And this is the same case for the dual ring as well. As you can see, there are two lines to the computer connect to the two rings here. One of the ring going on the right, another going on the left. This is a form of dual ring topology. So all of these topologies here uses what you call is a MAC protocol. So MAC protocol is a sublayer of a data link. As you can see here, there's a network, there's a physical network here, a physical layer, and there's a data link. Within the data link, there's a logical link controller. Right below it, what they call is a medium access controller, which is a sublayer. So MAC layer is a line between the network and the physical layer. Okay, one of the unique things about data link is that the data link has a MAC address. And then for the network, for the identifying each item, it uses an IP address. That's one thing unique about it. And each station shares a medium. Each station required to have a MAC address. So MAC address is, you could call it, each device is printed, make it from the factory. It prints a MAC address. In this case, it's a MAC address for your interface for your computer. Okay, let's talk about the logical link controller. So logical link controller is built on the top of a MAC server to provide medium independent communication service to higher layer. So whatever the higher layer is, it could be a TCP or UDP. LAC layer is provide interface or adoption, be able to communicate with the network layer more efficiently and effectively. That's the function of the LAC layer. LAC layer can appearance of a connectionless, connection-oriented services. A connectionless is basically treat each message independently. What happens is for the connectionless, it does not verify whether the packet received in the other side, properly or not. Okay, connection-oriented service, typically TCP is used in the network layer. It verify whether the packet has received in the other side using what they call as the acknowledgement. And typically, connection-oriented services uses TCP. Connectionless is typically used for UDP. When you look at the 802.802 standard for local area networks, which is operated by IEEE 802.802.org here, and there are a number of extensions, 802.1 local area for mature area network architecture. 802.2 LAC this is standards that describes the logical link layer, the function of the logical link layer. There is the 802.3 CSMA CD. We're gonna talk more about this. Basically, it's a medium, is carrier sense multiple access. What does it mean is it senses the medium, whether it's available or not. You better make sure that no one is sending anything that you can send. And the multiple access means a multiple workstation or can access this, but it can send one at a time, not all multiple parallel at a time. So carrier has the sense of whether it's available or not. So if it's available, it can sense the data. So another thing is collision detection, and quite often there's collision happens because there are multiple devices or computers trying to access the medium. there could be a multiple collision occurs, then there has to be some back off. They come off, then try that again. And this is a pretty standard protocol for CSMA CD for all the Ethernet access that it can connect to your computer, right? And a lot of you probably connect your computer through wireless, using wireless access point. And that for the wireless access point, that's what they call it is 802.11 wireless local area network here. And they use a CSMA CA, which is collision avoidance. It provide, avoid a collision, in first place. That's a CMS CA. Anyway, 802.4 is token bus, 802.5 is token ring. And, 802.6 is, there are a lot of extension. I'm not going to go into every one of this, and you should be able to find it and look through those different extension. 7 is a technical broadband cable. 8 is fiber optical local area network. And the 802.11, most of you pretty familiar with, is that wireless access point that you use regularly, probably every day. There are others, 802.12, 13. 802.15 is wireless person area network. That's for Bluetooth, some kind. There's a broadband 802.16, and what they call is WiMAX. They use 802.16 here, and the resume packet ring, the 802.18 regular technical advisory, and the 802.19 is coexistent technical advisory as well. So those are the different standards from the IEEE for local area network. Okay, there are other extensions that I have not mentioned in here. So now let's go back and see how does local area network, especially wireless, as develop in the first place. And especially the wireless arena. They first tried them back in 1970. University of Hawaii built the UHF ground packet. That was the first packet radio. For most of you, when you were little, when you use a walkie-talkie, right? Your walkie-talkie, talk to one person, another. That's not really a packet radio. That's more of a using analog to send the packet. What I mean is sending a more of a digital format, right? So at the time, they had a ground packet radio connection, to the computer, and the various islands in Hawaii. There are very different, different islands around Hawaii, right? There are a lot of islands using simple random access protocol. It doesn't think about it. It's simply randomly access the wireless medium, basically start sending, okay? And any station transmitter, whenever they have, regardless of other station, free for all, any frame overlap, they're destroyed, which means when the collision is destroyed, okay? A station will wait for random time, people try again, and loss of frame detect, but there's no acknowledgement within the time period. So what happened is, trying to send between the station, around different islands, it wasn't really successful because there were a lot of collision. You didn't know which station is sending, so there were a lot of collision, and that causes a very low throughput, which is only 18% or went through. Basically, that's pretty bad, right? So pretty unreliable. And next was they created a slotted Aloha, which in modification to increase the efficiency was, all stations are synchronized. Okay, so by periodic synchronization pulse, which means you can do round robin to send basically it has a slotted, basically you wait your turn, right? Each station wait its turn to send the packets to another station. So with that, each station has its own slot. With that, throughput has increased probably double, which is 36%. Okay, so that was really a big improvement, and from 18% to 36 when you use a slotted ALOA. Okay, so what they did was instead of just using slotted, I think that there has to be a mechanism to be able to detect the medium. If nobody's using it, then whatever the station be able to wants to send it can send it. So to do that, it needs to scan for the frequency and see is anybody sending or not. So that's why they created what they call this a carrier sense multiple access. It's a carrier basically sensing the medium, right? And there will be multiple stations, right? There are multiple stations, so all of them are accessing and trying to access the medium. So basically, you have to sense the sensor if there's anybody sending or not, right? You're at the classroom, and when you talk, you gotta hear and see, is anybody talking? If anybody's not talking, then you can talk, right? But sometimes, in some sense, there's nobody talking. The sum of two of you could be jumping and talking at the same time. That could happen. That's what they call this collision. Okay. So high rate of collision around due to the station ignoring other station. You shouldn't be doing that. So with the carrier sensing, station listens to channel before attempting to transmit. This is basically a listen before talk. So if channel is idle, then the frame is transmitted. If it's busy, channel will back off, right? Back off, it will not send, it will try again a little bit later, okay? So it's a big improvement over ALOA because no stations were transmitting at the same time. It checks for the channel whether it's busy or not. There are some collisions occur because, two stations trying to send it at the same time, that could cause some collision as well, okay? So, there are a family of a CSMA protocol defined by the rule. So the thing is, let's say medium is busy, okay? So let's, when channel is busy, you need to back off, okay? And it says back off. So how much do you need to wait? How much do you need to wait? So we don't know that, right? So what they did is there are different degree of persistence. So once persistent is this station is most aggressive. If it's busy, it checks again, it checks again, it checks again. It checks all the time. Checking whether it's busy or not. It checks all the time. And it takes a lot of resources to check all the time, right? But one good thing is as soon as it becomes available, then you can use the channel right away. This is more of the most aggressive way to doing it. Okay. The P persistent is basically you station tries again depending on the probability of P. The P of is probability of success. Okay. So you backs off, and what's the probability of success is high, then it tries again. So it does very randomly. Okay. Non-persistent is stations are not aggressive, which means is not just looking at the probability here, and it backs off for a long period of time and try back. The problem is it's very hard to find when each channel is busy. It takes a long time to do it. Okay, so they have done the study of sending through wireless and local area network through the air. Here is ALOA. Here's a slide. This is throughput. This is 100%. Nothing is over 100%, right? So this is one persistence. It's trying all the time. Okay. Throughput is this much, and the non-persistence is probably the highest. It tries not aggressively, not often. And this is more of a probability persistent. So as you can see, it takes longer time, right? Offer load, but it takes longer, and the throughput is high. Therefore, there's always a trade-off. Okay. So the thing is, there's a probability, persistence, when to try, and all of that. But another thing is they have included is CSMA CD, which refers to collision detection. Where, let me see here. While the transmitter station will listen. Why is it going over there? Okay. So station will listen for the collision, over immediately, listen while you're talking. Like I say, in a classroom, you got to listen. You say, no one else is talking, then you can talk, right? See, it's more efficient than CSMA because with the no collision detection, because there could be, a collision occur without the collision detection, right? After collision, stations back off at random and try it again. Maybe serious collision in one station successful grab the channel. When you try it completely, it should be able to grab the channel. Okay, so take a look at it for the CSMA. Here, the transmission, contention, and idle. There's a 3 different state. Okay. This is a transmission, it will detect it. This means it's busy. It's whoever sending it, it feels that there's a transmission required. I better not try it. That's collision detection. Okay. So here's the contention. Here's the number of slots. If it's a number of slots available, you can, the station can try it. If no station, and you try it. So these are the frames. There's a contingent slot, and these are the idle time. Okay, idle things, and nothing is being sent, right? Contingent, you got to grab the one of those contingent slots to be able to send it. Okay. So performance, it depends on on time to detect collision. If worst case probability delay between 2 stations with the collision detected time 2t. And so what happened is when they begin to transmit here, unless the station A, there's nothing is being transmitted, start sending it, send the signal. It takes time to get to the B, right? Before it gets there, it starts sending something else to the back to the station A. As you can see, there's right before it reaches, and and because the collision is happened, the collision is detected after 2t. Okay. Excuse me. Okay, and there's number of station and 2t length of the collision slots, the time to transmit frame, and time to transmit the frame, and otherwise, and it has to be a bigger than a time to transmit. Once this collision occur, you need to detect when there's a time 2t. The P equals the probability station will be transmit the idle time. So probability is a random probability. So you don't know when you're going to send it. So after successful frame, there's a contention period, series collision time slots. It will be end of a successful time frame. Exactly 1 attempt. Okay. So we need to figure out the length of the contention period. And equation is something like this. A probability of first attempt here is a P1 equals, what's the probability of successful first event. And the maximum occurrence is 1 over n. And P1 equals this. Mean length of contention period is J slots with collision either followed by one transmission, as you can see here. Okay. So also the maximum utilization is basically frame time plus contention period. On top is a frame time. Frame time over contention time plus the contention, and frame time plus the contention period. That's the maximum utilization of a medium. Okay. Let's take a look at this one. 802.3 CSMA CD is usually Ethernet, and predominantly it's a wire local area network. The CSMA came from, remember that in Hawaii, different wireless, collision and all that, but this one is applied in the more in the wired arena. And same is a very similar approach is being applied at the wireless area as well. Okay. And the 802.3 family is a family of a CSMA CD for 1001 to 1000 megabit per second. Utilization can be reduced by collision. Frames are designed to be long to maintain decent utilization. Also tends to repeat collision reduced by battery exponential backup as well. So when you talk about the binary exponential backup is contingent time slide equals 2t, nominally 512 bits time. After the curve conversion, each station is randomly choose one slot for next two slot, tries again. If there's a problem occurs, which means collision occurs, when is collision occurs, is randomly choose one slot, the next 4 slots. Okay, it basically when you randomly slot, they try again, and it's try within the next 2 slots. You try pretty quickly, but if there's a collision occurs again, then try next 4 slots. So you wait a little longer, right? Then it becomes longer and longer if continual congestion occurs. Basically, delay occurs. Okay, delays occurs. Okay. There's an exponential back off. This is what I mean is collision occur, you can try any of these 2 slots. If a collision occurs again, okay, it tries any of the 4 slots. If collision occurs again, collision occurs again, next 4 slots, collision occurs, and then you try 1 for 8 slots. So you expand, increases exponentially. So that means that there are a lot of congestions occurs. So it backs off, it becomes longer and longer, and pretty soon it's not after send. Okay. Let's take a look at the 802.3 frame format. Preamble equals 7 bytes of 101010 to synchronize the receiver's clock. There's a receiver's clock it needs to synchronize. The start of frame is basically indicating that this is a start of the frame. After that there's a destination address, where is it going to, and the source address is where is it coming from. And length is how long is this frame, and there's a data. And pad is and CRC to check where there's error or not. Okay, pad is basically used for make sure sometimes it has to be arrived at a certain number of bytes. Okay, in increment of 8 bytes or something. So if it's not increment of 8 bytes, you can use the path to make it a certain byte. Okay. So here's a description of frame format. Length of the data field. Data, typically is 0 to between 1,500 bytes. It's pretty long. Yeah, filler makes a frame at least 64 bytes. Okay, to make it. Yeah, CRC is an error detection. Okay. So this is 802.3. We talked about the CSMA CD. And how did the CSMA came about? So when you talk about the Ethernet, 3 megabyte per second Ethernet was invented by Xerox to connect, basically 1,000 station, 1 kilometer cable. It's currently 60 to 90, 100% are using Ethernet, right? So this is a long time ago. Okay, there's a 1980, the Ethernet version 2 is slight variant of 802.3 CSMA CD. It has a 2 byte type field instead of a link field, indicating the network layer protocol. And there's 8 bytes of a preamble, basically indicating that this frame starts at this point. Okay, so there are different types of Ethernet. There's a 10 base 5 or 10 megabit/second. 10 base 2 is a thin. 10 base 5 is thick. 10 base T uses unshielded twisted pair copper, and not many people use it right now. So 10 broad 36 uses a cable, TV coax cable, and the 10 base FB uses optic fiber and passive star. And typically uses a fast Ethernet. Sometime right now we are at the point using a 10 gigabyte Ethernet line, and this is fast Ethernet. So back in those days, it was considered pretty fast. Not anymore. It accelerated to 100 megabits per second to compete with the FDDI. That was a long time ago. It became obsolete, right? You can use a twist pair cable for passive start. It's not being used right now. Right now, is pretty popular is using a fiber to home. Okay, and So let's talk about the Ethernet hubs and switches. Hub is a central collection for cable or passive startup. Whatever the packet comes in, it sends it to everybody. It sends to everybody. When it comes in, it sends to everybody, right? And whenever it sends, it make a copy of it, send it to everybody. For the switch is different, right? When this workstation, sends a package to this switch, it sends to only to the destination station. Okay, so that's the difference between the hub and and the switch performance. So switch basically looks up the MAC address and to send wherever it needs to send. Basically, hub doesn't, right? You just make a copy and just send it to everybody. So in that sense, switch is more efficient because it does the filtering, but hub, when it sends to all the workstation, it has to do extra work to check whether it's this is for me or not. If it's not, just throw away. So just doing that, it takes uses of energy and what do you call it, very inefficient. So using a switch is more effective, right? Switch is basically a layer 2 technology. It's not layer 3. Okay. Let's talk about the talking ring. Okay, 802.5. We looked at the different topology of a local area network. Talking ring was one of them, right? Ring is basically beginning and is basically connected. That's considered as a ring, right? Rings are fairly bounded access delay. Token is a small packet circling around the ring. So basically what it does is each station needs to have a token to send anything. Okay, instead of filling the medium, whether it's busy or not, instead of doing that, it passes around the token. Okay, if you have the token, you can send the packets. Okay, when you're done with it, you send it, and next, workstation gets it and sends it. Okay. The typical token formats is there's a delimiter, is basically a starter token. There's access control, there's a control field, and there's end delimiter, which is the end of tokens. It basically look like this. Beginning and end, basically when is the beginning, when is the end. So if there's a number of bit token is bit is indicating it's a busy or free. Monitor bit station serving as token monitor will set this bit for busy token. When watches for token, there's always busy. There's also the priority 3 bits used for transmit data within priority. Priority doesn't used quite often, okay, and it doesn't being used. So and also the reservation is not being used as well. So in this case, today is I'm just relaying this to you to looking at the different technology instead of just detecting the business. You can use some form of tokens to be able to control the traffic and also manages who can send, who cannot send. So I'm just showing the technology. And actually, the ring is not being used quite often these days, right? So basically, use a CSMA CD or CSMA CA for wireless. And I'm just sharing this because this is another approach you can use to control who can send, who cannot send. Okay. So basic operation is station can transmit only by grabbing the free tokens. Okay, changes to busy token when it's being when is transmit frame change to busy and transmit frame after it. That means it's after you change to busy token, change to send it to others and indicating I'm using it. Nobody else can use it. Okay. Station with the destination address will read the frame circular back to the sender. Basically, it deletes, it sends the token and you change to free to busy, and you send it. All other workstation detects that and recognize that, oh, workstation A going to send it, so I better keep quiet, right? Then it come back to the sender, basically deletes it. Okay. It deletes it basically, and it sends the data. After that, it sends another token. It basically has a free. It sends it to the next one. Okay. Access control is basically this is 802.5. This is what the frames being used for the token ring. Access control, same as access control in token. Frame control is what type of it's a control frame, is it a data frame, those kind of things being indicated here. There's destination address, MAC address, source MAC address. Here's the data. This is variable, I think 0 to 1500 bytes, right? CRC to check whether there's any error in the frame or not, right? There's end of the field, frame status. So basically, frame status is indicating that the destination station set to 1 if frame has read it, and the destination set to 1 if the frame was copied. Okay, so what will happen is once it receives it, it can make a copy. So it's a 1, A equals 1, C equals 1. That means whatever the destination has read it and make it copied, then it's done. Okay. So sometime the destination station is down. Okay, and it's not able to receive it. Then in that case, it's A0. Sometimes destination is up, but not able to accept any of the frame. That problem occurs. Okay. So to token ring performance, when you talk about it, data frame followed by their cycle. T1 is every time to transmit the data frame. T2 is every time to pass the tokens from one station to another. So cycle is combination of a T1 plus T2. Okay, 1 equals frame transmission time is normalized. A equals propagation time around the ring. How long it took to go around the ring, and throughput is how much has to send it out. So propagation time is less than 1. Okay. So less than 1 is it starts a frame which is around the ring, and it's T equals A equals start of frame going to T equals 1 is a start station finishes the transmission, basically releases the token. That means the T equals 1 is it's busy, it's release 1 is finished, release token, then the next one gets it, does perform the same action. Okay, let's take a look at the let's see here. Yeah, T equals, yeah, okay. If it's okay, T equals 0, start of transmit frame. A equals sender receives the leading edge of frame, sender complete the transmit frame, goes to the next station. Okay. And the case A equals 1 or greater than 1, basically station finishes the transmission, release the token, start of the frame, which is around the ring, station releases token, it goes to the next station as well. Okay, this is the performance. Okay. Basically, let's wrap up. We talked about the carrier sensing in CSMA. Basically, started with the Aloha. There's a lot of Aloha, and there's a number of trials. They figured out that having a collision detection really improved the transmission of packets in the local area network, that including the wireless. And this has been used worldwide. We're using this today as well. Okay, the one good thing is there's a binary expenditure backs off, randomly. You can try again. It backs off randomly, and that's CSMA CD. That's really inefficient. And we looked into, once we back off, we come back again, try again fairly quickly. If it doesn't work out, you come back after longer period of time, right? So to have a fairness, between the workstation, this could create more of a starvation, I think. And then one workstation not have to send it because medium is channel is too busy. So there's what they call token guarantees a fairness and access delay, and we looked into a little bit about this. Okay. All right, everyone, I'm gonna just stop this, and thanks for listening, and I'll end this recording now.